Welcome back to another episode of Peter Explains Tech. In this video, we'll introduce you to the domain name system. So imagine this, you're on your laptop, in your web browser, trying to reach example.net. Both your computer and the web server for example.net are connected to the internet. Now usually your browser will automatically contact the web server for you and request the home page. Although you know the domain name, you have to remember that the internet runs on IP addresses, so you cannot just ask, hey, can you contact example.net for me? Because the internet can't, it only knows IP addresses. This is where DNS comes in. Think of it as a gigantic address book that tells you at which IP address any domain name can be contacted. To look up an address, you ask a special DNS server something like, who is example.net? And it'll tell you the answer. Problem solved, right? Not so fast. Remember that you're not the only one on the internet. There are billions of internet-connected devices that are also trying to look up IP addresses while you're doing the same thing. If we had just one measly DNS server to handle all of that traffic, it would be overwhelmed with requests immediately. Even if you added more servers, do we really want one organization to manage the entire DNS system? That's a lot of power and responsibility. I mean, if you sabotage this one organization, it's bye-bye domain names. It also makes the internet more susceptible to government interference, which traditionally tends to be a bit of a controversial topic. In reality, DNS is more of a distributed group effort. There's still a hierarchy to it, but responsibilities are divided. Let's start at the top with the root servers. There are over 380 root servers worldwide, and they're divided into 13 groups. Root servers know other DNS servers that can help you with specific top-level domain names. If you ask, who is example.net, it won't know the answer. However, it will know which servers are responsible for all the .net domains. We now have the IP address of a top-level domain name server for .net, so we can move on to step 2. We've arrived at the top-level domain layer of the hierarchy now. The way this works is that a bunch of servers are responsible for .com domains, then there's a bunch of servers for .org domains, there's a bunch for .ca domains, and so on and so forth. We're going to ask a TLD server for .net about example.net. Once again, we won't be getting a straight answer from the server yet. What it will give us, however, is a list of IP addresses of servers that are responsible for queries regarding example.net and its subdomains. We've arrived at the domain name layer now, and rest assured, this is in fact the final step. For the third time already, here's that million-dollar question again, who is example.net? And yes, this server will give us the right IP address. The web browser can now try to contact example.net's web server using this IP address. Let's recap what just happened. A root server told us which DNS servers are responsible for .net domains. A top-level domain server told us which DNS servers are responsible for example.net. And finally, one of example.net's DNS servers told us which IP address is associated with example.net. After people make their way through this maze of DNS servers, these are the servers that have the IP address we're looking for. They're said to be authoritative servers for example.net. We've covered the basic idea of DNS, but we kinda glanced over the details. Time now to take a closer look. Somewhere on this planet, a user's trying to go to example.net in their browser. Before the browser can contact the web server for example.net, it needs to find its IP address. And to do this, it'll perform, you guessed it, a DNS lookup. Instead of doing the heavy lifting itself, your computer will hand off the request to your local DNS server. This server will play the DNS client on your behalf and send you the answer when it's ready. The first thing the DNS client will do is contact a root server. The client comes pre-equipped with a list of root servers as well as their IP addresses. If the client didn't have this list of root servers, it simply wouldn't know where to start looking. The client picks a root server at random and starts looking for the domain name. Its query will look a little something like this. The first field of the query is the domain. Since we're looking for the IP address of example.net, that's what we put in our query. Although the root server won't know the answer, it will be able to use this information to refer us to an appropriate top-level domain server. The second field is the DNS class. This field can have a bunch of values, but it is almost always IN, which stands for Internet. The third field tells the root server which type of result we're looking for. We ask for type A because we're looking for the address of a top-level domain server. The root server will then prepare a response. Here's what it sent to us. As we expected, the root server refers us to the top-level domain servers for .NET. The first section contains general information about these servers. This is the time to live, which indicates how long the information remains valid. The value is specified in seconds, so this information is good for 2 more days. Field number 3 is the DNS class, which once again is IN for Internet. Field number 4 is the record type. The NS stands for name server. This indicates that this record points to a DNS server that is authoritative about hosts in the .NET domain. This is the root server's way of saying, I don't know anything about .NET domains, but go ask that guy. The last field contains the domain name for each of these name servers. Now, with the domain name alone, we can't reach these DNS servers because we need IP addresses. This is where the additional section comes in. Also called glue records, these tell us where to find the domain names that were previously mentioned. They're not always present, but sometimes they're necessary. Like, if we didn't have this information, we'd have to look up m.gtld-servers.net first. But since we don't have the IP address of any TLD server for .NET, we can't look up .NET domains, so we're stuck in a loop. This is why the glue records are absolutely necessary here. Using the IP address we just obtained, we can contact a TLD server for .NET domains now. Although our query remains the same, the response will be different. Servers at the TLD layer have more specific information about our target, so they'll bring us closer to the answer. The server crunches some numbers and sends back the following list. The authority section reports 2 name servers for example.net, a.iana-servers.net and b.iana-servers.net. We'll just go with the first name server and retrieve its IP address from its glue record. Note that there are actually 2 glue records for this name server. The second one is a quadruple A record. From this record, we can obtain its IP version 6 address. We'll just stick to IP version 4 for now. On to the next DNS server. We will reuse the same query, but the response will look a little different this time. Let's see what we have here. For the first time, there will be an answer section. From there, we learned that example.net is at 93.184.216.119. The authority section tells us which name servers are authoritative for this domain, but that information is no longer relevant to us. The local DNS server can now send back the information to the computer that requested it. That information goes to the operating system, which now knows where to find example.net. Then the browser can contact the IP address, request the web page, and we're done. A couple more facts about DNS servers. One IP address can house multiple physical servers. For example, Facebook's name servers only have 2 IP addresses, but that doesn't mean that they only have 2 physical name servers to serve everyone worldwide. By spreading incoming requests across multiple servers, they prevent them from getting overloaded. This is true for servers in general, by the way, whether you're talking about web servers or mail servers or DNS servers. One name server can be authoritative for multiple domains. For example, the organization behind Wikipedia uses the same name servers for multiple domains, including wikipedia.org, wikimedia.org, and wikibooks.org. Another example of this is when you register a domain name. In most cases, your domain name will use the name server of the company that hosts your website for you. Before I wrap this up, I want to share some more useful DNS features with you. The first one is caching. Remember when we got that answer back from the authoritative name server? Well, as you may recall, the second field in the record indicates how long the information remains valid. The server specified a time to live of little more than 86,000 seconds, or as normal people would probably say, 24 hours. Instead of looking up the answer every time we need it, we can save this piece of information until the next day. This eases the load on the name servers, but it also saves us precious waiting time. DNS has support for both iterative and recursive queries. Iterative queries look like this. You consult a root server that will refer you to a TLD server. The TLD server will refer you to an authoritative name server. That third server should be able to give you the answer. Iterative queries are all about actively seeking out all the information yourself. Now, recursive queries, on the other hand, are structured a little differently. First, you ask a server a question. If they don't have an immediate answer for you, they'll go ask someone else in your name. That server in its turn may ask another server, and finally, the answer comes all the way back to you. In a recursive query, servers will try to gather information from other servers if they don't have the answer themselves, whereas in an iterative query, the client has to piece together all the information on its own. In real life, a mix of iterative and recursive queries is used. The most common scenario is that your computer will send a recursive query to your local DNS server. This local DNS server will then handle the query iteratively, piecing together information it gathers from root servers, TLD servers, and authoritative name servers. Once the local DNS server knows the IP address, it can respond to the computer's recursive query. Our introduction to DNS ends here, but there's lots more to learn. DNS has some security flaws, so hackers can abuse it to redirect people from their bank's website to a malicious site, and you won't be able to tell by looking at your browser's address bar. If you want to learn more about this and get a little too paranoid, look up DNS spoofing. DNS also plays a role in the routing of emails. If you want to find out how that works, look up MX records. The MX stands for Mail Exchange. And with that, we wrap up another episode of Peter Explains Tech. Thanks for watching. See you next time.